on southern Ocean and some of the data from the Bay of Bengal, looking at the discharge of Indian rivers into the eastern sector of the Bay of Bengal, mostly during the monsoon. So without ado, let's get started. So forams come in different shapes and sizes. I don't need to tell this group about different shapes and sizes of forams. I can barely recognize them. But most importantly, they are single-celled organisms, and yet they form a calcium carbonate shell around them, which is 99% pure calcium carbonate. And it's the 0.1% impurity in that calcium carbonate that we non-traditional geochemists are interested in. Now, when we talk about foram geochemistry, we have to tip our hat to Cesare Emiliani. This is a picture of Cesare talking to Harold Urey, and Jerry Wasserberg is sitting in front of them. But it's also an indication of how foram geochemistry has been in vogue for the last 70-odd years. And what I want to draw your attention to is that Cesare analyzed 3 samples for delta 18O and got a science paper out of it. Gone are those days. The next guy who kind of revolutionized foram geochemistry in terms of the stabilized foram geochemistry is Nick Shackleton. This is his classic 1967 paper, where he introduced the idea that the foraminiferal delta 18O, which is not only recording the seawater temperature, it's also recording the waxing and waning of polar ice sheets, because as ice sheets grow, seawater become heavier, and ice sheets melt, seawater become lighter. And bottom right corner, we have the Godwin lab from the, I would say, early 2000. You can see Luke and Steve Barker standing behind. Simon Crowhurst is there. In the front row, Pallavi Anandar is there, Marilyn, Nick himself, then Van Handel, Harry, and all the usual suspects are there. Now, my interest is not in the oxygen or carbon isotope systematics. My interest in this component of seawater. If we take a kilogram of seawater, we have around 34.4 grams of salt. And in that 34.4 grams of salt, less than 1% is the others, which contains boron, lithium, barium, all other elements, which I am interested in. Now, Lennart's work kind of summarizes what happens when forams calcify. If we take seawater, and if this is the salt content of seawater, it's dominantly controlled by chlorine and sodium ions. Now, when you precipitate inorganic calcite out of that seawater, what you observe is that that inorganic calcite is rich in magnesium and much depleted in other elements. Whereas when forams calcify, that inorganic calcite is strongly depleted in magnesium. The sodium concentration doesn't change much. The strontium concentration actually goes down. So divalent cations are discriminated against by forams. Sulfur concentrations are unusually high compared to what we could observe. Now, there are 2 possible pathways by which foram calcification has been talked about. The first one, the transmembrane transport proposed by Gernot and Gerald, talks about how calcium and DIC are selectively transported to the calcification site. And the other one is the vesicle inclusion and then exclusion of dissolved ions, proposed by Jonathan Harris and co-workers, talks about how vesicles, seawater vesicles are captured, and then they exclude magnesium ion from that system. And also Lennart's work has shown that when calcification happens, the pH is upregulated. Now, why am I talking about these things? Because all of these phenomena, whether you're moving ions across a membrane, or whether you're excluding a particular ion, whether you're upregulating the pH or downregulating the pH, will have a consequence about the distribution coefficient of elements into the calcite lattice. Okay. Now, moving on to the next one. We can see that in Foraminifera, the impurities that we are interested in are not homogeneously distributed. What we have here is a thin section of Orbelina universa sample, which is around 5 micron in this width at the bottom, and then it tapers into nanometers scale. And this is Oscar's work, where he did X-ray diffraction on them. And you can see the magnesium banding in Orbelina universa. You can see the magnesium banding in Amphastigina. So the impurities in the shell are not uniformly hosted, which begs a question. So whether or not the chemistry of the shell is going to be representative of its growth environment or not. However, when we look at bulk foraminiferal chemistry, we can faithfully reconstruct parameters like temperature, carbonate ion concentration by looking into foraminiferal trace element values. On the left, we have Pallavi Anand's magnesium calcium to temperature calibration, for multiple different planktonic species. On the right, we have the compilation of boron-calcium to carbonate ion saturation values from Jimin Yu and James Ray's work. And overall, the correlations are robust, and it has been time-tested over multiple publications that these correlations hold. So forams are a faithful archive of seawater as long as we ensure that we are dealing with a size-specific approach, we go for a species-specific approach, and there is chemical cleaning and visual checks. The imperative nature is the visual check. We have to check for diagenesis, we have to check for presence of silicate material and other substances. Now, the foram that looks really shiny is a living foram, which has the symbionts on its spinels, and it's doing its business for a month. But when it dies, the spinels are lost, and they look like this. And the unclean forams, you can see the impurities present in a fraction of unclean foram. So how do we go from unclean foram to clean foram? This is a picture of a Menardi, if I'm not wrong. And you can see the calcium carbonate overgrowths on it and the iron manganese overgrowth on it. Now we have to go from this Menardi to a much cleaner version of it. From this type of material to this type of material, which looks absolutely pearly white. Now, the main mechanism behind that is chemical cleaning, and this process was kind of established by Steve Barker with Mervyn Reeves. And we need to also acknowledge the fact that Ed Boyle and his group with David Lee and Yair Rosenthal had been working on it. Now, the key point here is that there are two types of cleaning process that we can adopt. The magnesium cleaning process, which usually only takes into consideration oxidative cleaning to get rid of the organic matter, and the cadmium cleaning, which takes into consideration the hydrazine-based reductive cleaning to get rid of the iron manganese oxides. Now, if you plot the same samples which were cleaned oxidatively only and reductive oxidatively, you can see there is a bias in the magnesium calcium value towards the oxidatively clean samples. They're giving you higher magnesium calcium value. Why? Because the high magnesium calcium is prone to dissolution, and the reductive cleaning is much more aggressive. It's much more acidic in nature, so there is more calcite loss during reductive cleaning. This is going to be important when we get into the barium-calcium work, because barium-calcium, to do proper barium-calcium concentration on Foraminifera, we have to get rid of the iron manganese oxide hydroxide coating. Strontium-calcium doesn't have a significant impact based on the cleaning, so it's a safer bet to work with strontium-calcium on that space. Now, the way we analyze forams in our lab, we take the foram samples, we crack them open. We don't crush them open. Every literature talks about crushing them open, and if you crush them open, you won't have anything left at the end of the day. We have a reductive cleaning step and an oxidative cleaning step, followed by an acid leach, which gets rid of the adsorbed cations from the surface. Then you dissolve in a small alicot. Boron is microdistilled. We take advantage of the volatile nature of the boron to separate it from the matrix, and the matrix which is left behind can be used for other isotopic analysis. And a small alicot of the dissolved samples is taken out to first measure calcium concentration on the ICP-OES, and then trace element concentrations on the ICP-MS. Now, what we're going to focus on is this little purple box, the boron, the barium, all the little stuff in the small fraction of the impurities. Boron has two isotopes, 10 boron and 11 boron, with an abundance of 20 and 80% respectively. Seawater boron isotopic composition is extremely homogeneous. This is all Gavin Foster's work. And it has a very long residence time. So for all practical purposes, if you're looking at a process which happens over a million years or a few million years, you need not worry about the changes in seawater boron isotopic composition. Now, the boron in seawater speciates between borate ion and boric acid based on the pH, and only the borate ion gets taken up by the biogenic calcite. So the boron isotopic composition of biogenic calcite should represent the borate ion isotopic composition of seawater, which in turn is a function of pH, since the boron isotopic composition of seawater is constant. Now we can look at it in a bit complex way, where, hang on a second, let me try and get this thing minimized. Okay, better. On the right-hand side, we have the seawater pH in x-axis going from 6 to 11, and delta 11 boron of speciation of boric acid in blue and borate ion in red. In the bottom right-hand plot, we have the speciation in terms of concentration, same idea, boric acid in blue, borate ion in red. So as pH increases, the solution becomes more and more basic. The boric acid dissociates further into borate ion. This is because of the fact that there is H plus ion associated with this equilibrium. The more the H plus ion, more the equilibrium is pushed to the left. So lower the pH, more the H plus, more abundance of boric acid, less dissociation. But at low pH, we have all of the boron mostly contained as boric acid. So isotopic composition of the boric acid is exactly same as the seawater. As pH increases, the fractional contribution of borate ion increases, and so its isotopic composition also increases. And this is the range in which foraminiferal or seawater range of pH that we observe in the modern day. And it is expected that the foraminifera incorporates boron along this pH range. So you have a sharp change in borate ion isotopic composition across this range. So you can utilize it to constrain pH to a degree of almost 0.1 per unit. So moving on to the fact, for any species-specific approach, we need calibration. On the left, I have Michael Henahan's 2017 work on Orbilina universa, where the one-to-one line between delta-11 boron of calcium carbonate and delta-11 boron of the borate ion isotopic composition in the solution is given in the black line. But the cultured samples are falling parallel to that black line, but slightly offset. There can be a magnitude of reason for these offset because each foraminifera calcifies at a certain different rate, and depending on the size fraction, the growth rate is different. So one of the theories that have come forward is that Takashi's work has shown that forams are actively pumping proton out. So the pH of its microenvironment is not exactly the same as the pH of its ambient seawater. However, if this offset between this pH and the ambient seawater is constant, we will have a constant offset between this one-to-one line and the calibration line. And what we have observed for multiple species that this calibration is different, but it's always linear. So thus, planktonic foraminiferal boron isotopic composition is a faithful proxy for reconstruction of the borate ion isotopic composition of the seawater. If you have temperature, salinity, growth rate kind of information handy. Now, when it comes to boron, I need to acknowledge these two people, Barbel Hornish and Gavin Foster. They have been pioneers in the field. Before them, Abhijit Sanyal did a lot of pioneering work with Gary Hemming. So much of the work that I have done is based on their initial work and following up on that. So what we did, we tried to constrain the carbon dioxide exchange between seawater and the atmosphere in the southern hemisphere. Now, main CO2, which is being in the atmosphere, is equilibrated with the surface ocean. And there is a large amount of CO2 stored in the deep ocean, which is usually out of organic matter oxidation. Now, when we talk about glacial interglacial cycles, as we have here, time moving from right to left around 1.8 million years to modern day, the glacial interglacial Delo18 values are given in blue line, where heavier values are at the bottom and lighter values are at the top. So if the isotopic composition of the benthic foraminifera is light, it's a hotter climate with less continental ice. And if it's heavier, it's cooler climate with more continental ice. In the bottom green line, we have the PCO2 concentration of the atmosphere as reconstructed from the Antarctic ice cores. And you can see that the PCO2 concentration and the glacial interglacial cycles are co-varying. High PCO2 concentrations are attributed to interglacial climate, whereas low PCO2 concentrations are attributed to glacial climate. So there is a direct correlation between atmospheric CO2 concentration and global temperature. We all know about that. This is a direct greenhouse effect. And other than that, the pacing of these cycles are based on Milankovitch cycles, which is the Earth's orbital motion around the sun, and we have limited control over that. CO2 is the one factor that we can control. So what we're going to try and do is constrain the CO2 degassing rates during the last termination from last LGN, which was around 20,000 years ago, to Holocene around 8,000 years ago. Now, this is Antarctic ice core's CO2 record given in yellow circles. The Antarctic ice core temperature record is in red, and the global temperature record is in blue. This is from Shakun's work. This is a classical work which shows that the CO2 is actually leading the global temperature rise. So first you have a CO2 rise, then you have a global temperature rise. And if you subdivide these proxy values, these are the proxy values that he had compiled, between the southern hemisphere and the northern hemisphere, southern hemisphere in red, northern hemisphere in blue, in the northern hemisphere, temperature is lagging CO2. So CO2 is leading temperature. Whereas in the southern hemisphere, temperature is leading CO2. So with this information, what I'm going to try and do is try and constrain the amount of air and seawater CO2 exchange that happened during the last termination in the Southern Ocean. So in the modern day, what we observe that the equatorial Pacific is a large source of CO2, and most of the reconstruction of past CO2 exchange is constrained mostly to the equatorial oceans. We have the Indian Ocean data, we have the Atlantic Ocean, we have the Pacific Ocean for the last 35,000 years. This is compilation from Tariq's work. This is not Tariq's work. He had compiled the work. I've just stolen this graph from him. So mostly it is the equatorial ocean, but there are some glimpses of Southern Ocean degassing. Why Southern Ocean? In the modern world, Southern Ocean is the only 360-degree ocean. We have very low chlorophyll concentration in the Southern Ocean. However, it is very rich in nutrients. Phosphate concentration is one of the highest. So it's a high nutrient, low chlorophyll zone. So which means there is constant upwelling of deep nutrient-rich water, which is bringing CO2 to the atmosphere. However, if you start supplying this system with enough iron, which is modern-day iron limited, much of that CO2 will not be degassed, much will be captured and taken down. So what we're going to try and see is how at termination 1 this system works. And Southern Ocean in the Indian sector doesn't have any existing records of CO2 degassing from the glacial interglacial time period. So moving on, what do? You find a grad student who is motivated enough, put him on a boat, send him to Southern Ocean, get a sample core, and get him to develop a method to analyze boron isotopes. So Satya went on the cruise, NCPR cruise to Southern Ocean, and we collected a core from the 45 degrees south, around 2 degrees east. This is around 3,000 meters of water depth. Now, this particular site sits away from the polar front in modern day, but what we have to be cognizant of that the polar front will be migrating during glacial interglacial cycles. Okay. Now, in terms of the methodology, Satya analyzed a lot of seawater samples and a lot of in-house coral standards. The seawater values is spot on with what Gavin's values are, and the coral standard values give us a precision of around 0.44 per mil. And we have been able to do it over a large range of concentration of boron. So which means that the method has been robust. When it comes to any foraminiferal analysis, we're going to use an error bar of around 23 ppm in CO2 space. How did we get to that? We had a large pool of Urbalina Universa samples from the core top, and we divided it to 7 aliquots. Each alicot was cleaned separately, analyzed for boron isotopes separately. We reconstructed pH from that. The only assumption was that we took a constant temperature and alkalinity for this pH reconstruction, from pH to CO2 reconstruction. And we can see that the CO2 uncertainty is around 23 ppm. So the CO2 uncertainty for all the reconstruction will be around 23 ppm. Now, what are the preliminary observations of this core? There is a near absence of benthic species, and the bulloides and inflata dominates, which is indicative that this is a strong upwelling region. And the region, the length of the core over which the data has been generated is between 36 centimeters and 100 centimeters. Why? I'm going to come to that later, but we're going to be working with these two species, bulloides and inflata, the surface dwelling bulloides and the lower mixed layer dwelling inflata. So if there is a strong upwelling, inflata should register a lower pH, which is high CO2 enriched water, whereas there is weak upwelling, the difference between the PCO2 values or the pH values between these two species should diminish. The C14 ages came out like this. There, beyond 36 centimeters, there was an age inversion, so we have discarded that side of the core. And between 36 and 100 centimeters, we have a time period going between 13,000 years to around 19.5 kiloyears. So time will be moving from right to left. And this is the oxygen isotopic composition from the inflata. You can see the glacial interglacial transition at around 18 kiloyears. This is the delta 13C. There is also a sharp change in the delta 13C in inflata at the glacial interglacial transition. Now we're going to slowly move into the magnesium-calcium space. Magnesium-calcium, as we know, is a proxy for temperature. The Delo 18 curve will be given in gray line. It's in an inverted axis. So lower values are heavier composition, around 3.6. Lighter values are on the top. So one thing to notice per se is that in the last part of this transition, in the Bowling-Allen rod, magnesium, calcium, and Delo 18 are completely decoupled. Magnesium, calcium in that particular site is showing a cooling trend both for boloides and inflata, whereas Delo 18 values are showing a warming trend. During the transition, we have a magnesium values in boloide space which are going slightly warmer, and then again cooling down. Heinrich stadial, we don't see much. This has remained cold in the boloide space. And there are two pulses of warming which we observe here. In the inflata space, we have much more sinusoidal warming events matching up with Delo 18 events. Now we're going to move on to the delta boron. The raw delta boron of the calcite looks like this. There's a large scale variation, pretty low values. Keep in mind that calcite and the borate ion of seawater are not the same. We have to use species-specific calibration to bring the calcite delta 11 boron to seawater borate ion composition. So utilizing the calibration curves for boloides and inflata, we get adjusted delta 11 boron values or the borate delta 11 boron values in the solid lines, whereas the dashed lines are the calcite delta 11 boron values. When we convert, so this is what the borate values look like. So in boloide space is varying between 15 per mil to around 18 per mil. And in inflata space, it's varying between 15.5 per mil to 17.5 per mil. And we convert them to pH. The pH range is between 7.8 and 8.2 for boloides, and inflata it's between 7.8 and 8.1. And PCO2 reconstruction, keep in mind, we are looking at pre-industrial PCO2, surface ocean PCO2 value. Surface ocean PCO2 pre-industrial should be around 180 ppm, which means the equilibrium values are all outside of this axis, which means at any given point of time, the Southern Ocean surface water is supersaturated with CO2, so it has a potential to degas CO2. Why I say potential, why I'm not saying that it is degassing, I'll come to that later. First thing to observe that during the last glacial transition, we have a very large pulse of CO2 in the first phase. And then there is another pulse of CO2 at around 18 kiloyears, clearly visible in boloides. Heinrich stadial 1 kind of strangely shows a rise in PCO2 concentration of the surface ocean, whereas Bowling-Allen starts with a PCO2 rise and there is a gradual decrease after that. Whereas in inflata space, what we observe is there is a rapid rise in PCO2 concentration of the surface ocean, the weak mix layer, during Heinrich stadial 1. And during Bowling-Allen, there is a gradual increase in the PCO2, which will be in lieu with what we observe in CO2 space in the Antarctic ice core records. Now, moving on to the next, remember, we have the CO2 coming out before the global temperature change. And the southern hemisphere, in the southern hemisphere, the temperature leads CO2. So the first, there should be a temperature change, then there should be a CO2 change. And when we compare only the boloides, magnesium, calcium to PCO2 values, what we observe is that we don't observe any clear trend in the Bowling-Allen rod. Firstly, the magnesium, calcium is cooling, whereas the PCO2 values are going up. In terms of Heinrich stadial 1, we don't expect to see any large-scale cooling in the southern hemisphere, but it still remains cold. PCO2 values have gone up. And there are pulses of large CO2 excursions during the transition between 19 kiloyears to Heinrich stadial 1, which shows that the Southern Ocean has played some significant role in terms of global CO2 rise during transition 1. And when we move on to the inflata space, same exact observation for Bowling-Allen, there is a sharp cooling happening over this period of time. However, the CO2 degassing over this period of time in inflata space shows much stronger CO2 degassing, which will be equivalent of stronger upwelling to the surface. Now, why would the inflata and the bolloides be decoupled. Firstly, high PCO2 in the mixed layer is not indicative of high CO2 degassing, because much of the CO2 can be sequestered back as organic matter into the ocean system. Now, we do find a consistent evidence for increased degassing during high stadial 1 for both surface and mixed layer species. And the cooling trend in magnesium-calcium space for bowling alley is ubiquitous for both inflata and bolloides. Can that be a question of changes in the polar front? But we do find a significant degassing between the bowling alley rod. Okay, so that is the kind of state we are in for the Southern Ocean work. We are in the process of calculating the total CO2 flux. And after that, it's a question of Satya writing up this paper. Now we're going to move on to the second part of this talk, which is the barium-calcium part of the talk. Now, barium-calcium has been recognized as a proxy for continental runoff. This is David Lee's work with the West African monsoon. What we have here, time going from right to left, from 24 kiloyears to modern day. Magnesium-calcium, barium-calcium reconstructed from Ruber species, sea surface salinity, and delta 18O of the species, and northern hemispheric delta 18O record. What we observe that during the glacial to interglacial transition, there is a rise in the barium-calcium value as expected with an increase in continental runoff with the intensification of monsoon. But Younger Dryas shows a rapid crash in the barium-calcium, which is also imperative because if you cool down the globe, there is less water there is less moisture in the atmosphere. As a result, there is less continental runoff. And as soon as we recover, there is a rise in barium-calcium. Now, what Sudhir has been trying to do, he's a postdoc with me, is reconstruct the barium-calcium record of the Bay of Bengal for the last around 140,000 years. Now, just a quick introduction to the Bay of Bengal. This is India, the riverine systems of India given. And this is a salinity map of Arabian Sea versus Bay of Bengal for the month of January, with wind patterns not bringing monsoonal rainfall towards the subcontinent. Now, as soon as we move into the month of July, where you can see that the winds are bringing in moisture towards the subcontinent, you can see that extremely low salinity zones coming up towards the river mouth. We have the Ganges-Brahmaputra system, we have the Mekong, we have the Irrawaddy, all of the major rivers bringing large amount of fresh water to the Bay of Bengal system. So with the overview like this, if we take the January months in the top set of panels and the July months in the bottom set of panels, we're going to go from salinity to silicate to nitrate to phosphate for January, and then in July, salinity, silicate, nitrate, and phosphate. We don't need to look at through a microscope to understand that there is a huge flux of silica coming out of the river mouths. There's a huge flux of nitrate coming out of the certain river mouths. And there is a certain flux of phosphate in this region, mostly due to upwelling. Now, from this information, what Sudhir wanted to do is use leg 353 samples from site U1446 to reconstruct the barium-calcium story of the past ocean. Now, this is what the barium-calcium record looks like. So he's got two different types of foraminiferal cleaning involved, reductive oxidative cleaning and oxidative cleaning. For most part, the reductive oxidative, for paired samples, the values are matching up. But in certain cases, what you can see that the values can be different. So we're going to stick mostly to the reductively cleaned samples for the entirety of the record. The record has been split in two sections now. On the left, we have time going from 70 kiloyears to modern day. On the right, from 130 kiloyears to 70 kiloyears. The top part is the delta 18O of G. Ruber from Clemens's 2021 paper in both panels. We have the salinity next. We have the barium-calcium from previous publications. We have the present barium-calcium from the present study. We have the percentage of G. bolloides and cadmium-calcium, which is a proxy for productivity. Now, if we focus on the barium-calcium from the two studies, what is clearly obvious that in the late post-deglaciation, there has been a rapid rise in the barium-calcium. Similarly, there has been a rapid rise in cadmium-calcium, which is indicative of increase in primary productivity. Now, the glacial period, as what we call it, the transitional glacial period, we will see that the barium-calcium is low, productivity is low. However, if we go back in the past, what we observe is that there are other places where the cadmium-calcium is low, also the barium-calcium is low. So there seems to be some sort of coupling in the system. We are trying to fill up these data sets to have a much more higher resolution barium-calcium. But what is obvious is that a rise in barium-calcium doesn't correspond to a rise in cadmium-calcium. So there can be some decoupling between productivity and runoff. So what we want to constrain is that with a high resolution record, whether the productivity and runoff are going hand in hand, or whether there is a strong decoupling between productivity and runoff, depending on whether you're a glacial cycle or an interglacial cycle. So that will be the last phase of this work. So I think I've finished on time. I've got plenty of time for questions.
Yeah. So thank you so much, Sambuddha, for such a nice talk. So yeah, we are now open for the question. So if the audience is having, if people are having some question, you can ask directly, or you can write in the chat, and Sambuddha can read it, or I can actually translate that one or two. So yes, any question? So but there are a message like, thank you for this clear and nice presentation. And thank you. It was super interesting. I learned a lot. No question?
That's very good. Nobody is asking me questions.
Yeah. Babette is there, I think.
Yeah, I have a question.
Sure,
Sambuddha, are you thinking about, does this core also have a Holocene?
This core doesn't have a Holocene because this was a meter-long core, and beyond 36 centimeters, there's an age reversal, which we think is a slumping event. This is at the Kerguelen Plateau, so it doesn't go back. But we are definitely going back there to get more cores to find the Holocene.
Okay. Okay, so this was just 1 meter.
This is just 1 meter. It's a gravity core, just 1 meter.
All right. Well, that's quite a lot of analysis have been done on it. That's quite funny.
And a centimeter interval. Yeah.
Yeah. Okay. I think Gavin has a thought.
Gavin has a question. Hey, Gavin. We just got the standards, and we are going to analyze it. Hopefully, by the end of the month, I can share some data with you. It'll be interesting. Yeah.
Yeah. So, Sambuddha, there is a question. Will you check it from message, chat,
I'm looking
or
at the chat. Yeah.
Yeah.
Gavin had a
Okay.
question. I answered that. And this is a species-specific calibration that Satya used. I think it's either from Michael's work or somebody from Gavin's group, most definitely. I should be knowing it. I'm sorry, I don't recall the exact paper.
There is this last question also. There is another question, I think. Cesar actually asked that question. Thank you.
Yeah, I answered that. Yeah.
Could I ask another question? And I have not worked with boron and all, so I could be completely ignorant. But I'm just wondering, has there been a study where you've looked at lots of different core tops from all over the world to kind of see, you know, how the contents, you know, the CO2 contents kind of for the Holocene, how if that kind of fits with what we kind of know, see, and stuff like that?
So Gavin did one of the Babel did a bunch of work, then Gavin did a bunch of work, then James did a transect where he did the core tops to prove that it's matching up with the modern ocean. And but at the moment, I think it's one of the most well-established CO2 proxies. If you measure it right and if you have the right core, then you'll get the right number for PCO2.
Okay, thank you.
So, Sambuddha, there is a question from Rohan.
I'll get to that. Rohan, density stratification, can it alter the proxy? More than density stratification, see, salinity has a minor effect on boron isotopes, though it does have an effect on magnesium-calcium ratio, which in turn gives me the temperature, which is also used to calculate the PCO2. But for boron isotopes, temperature will have a more significant effect because the equilibrium is temperature dependent. So thus getting the magnesium-calcium number right and the conversion of the magnesium-calcium temperature right is also very important.
Okay, any more question? I don't think there is no more question. So, Sambuddha, I am having a question. Okay.
Sure.
So, yeah. So, like, what I understand, though I am not a very known to these geochemical proxies and all, but what I understand that all those data are like up to 18 million year. So, what do you think that these sort of data can be used, or you can use this boron isotope for a, like, I work in Eocene, Paleocene time. So, is it possible to use those data for that
Most
time?
definitely, if the preservation is good, you can use it there. But you gotta have some sort of model for alkalinity and seawater boron isotope ratio, which I think the Foster group has been working on for a long time. So we have got a ready-made cookbook to go to for that. So deep time, definitely this can be doable over short intervals where we know boron will be conservative in seawater, and they are definitely possible.
Thank you.
Sure.
So I think there is no more questions. So over to you, Babit.
Sorry, Sambuddha, if you could share the screen. We just have one more screen to share that Ubashi, I think, is going to put up. And that's just about the next month's meeting. So we're very pleased to announce that. So first of all, thanks very much, Sambuddha, for a great talk and showing lots of new data. And I think it's nice to show sometimes also if you don't know exactly what it says, you know, everybody goes to these things, you know, trying to understand their data and stuff like that. It's nice to be honest about these things. So next month we have Joachim Schönfield from the GEOMA in Kiel in Germany. And he's going to talk about benthic foraminiferal patchiness. So the seminar will be on the 18th of October at 4 o'clock European time. So if anybody has any further comments or questions, please shout out. And otherwise, we're going to end the meeting. And Sambuddha, if you just could stick around for a couple of minutes, that'd be great. Then I wish you all a wonderful week and see you later. Taking a while for people to go.
Babette, has the term started for you, or is it still?
I'm very lucky. I'm on a fellowship, like a 7-year fellowship. And I've not had to teach for the last 3 years. I've got still 1 year. I don't have to teach. But next, I'm doing a little bit of teaching.
You're making me envious.
Yes, but no, I do a little bit of teaching, but